Hello everyone, welcome back. In previous lecture, I explained about the theories of slip line, the introduction and the derived equation for the same. Today's lecture, I will discuss about the upper bound theorem and lower bound theorem, and this is the last lecture of this subject. So let us start with the upper bound theorem. Now, in upper bound theorem, when a body is undergoing plastic deformation, its various particles moves with respect to one another under the action of external forces. Therefore, a velocity field is created in the deforming body. There is velocity field as I explained in the previous lecture. At the 45 degree there was the hodograph which was showing the velocity field. However, this actual velocity field is unknown to us. We assume a suitable velocity field which satisfied the boundary conditions and incompressibility condition. Now, according to upper bound theorem, the rate of energy dissipation calculated from the assumed velocity field is always higher than that by the actual velocity field. So here there is two things. First, we have to calculate the rate of dissipation of energy from the assumed velocity field is always higher than the actual velocity field. So there is two. First one is assumed velocity field and second one is the actual velocity field. So for both rate of dissipation, and the upper bound theorem says that the uh, assumed velocity field is always greater than the actual velocity field. Therefore, the die load calculated from the assumed velocity field is always also higher than that due to actual one. So die load will automatically become higher for the actual velocity field. And the statement of upper bound theorem is as that the of all kinematic admissible velocity fields, the actual one minimize the function, that is one function j dot, where this is equal to 2 by root 3 integration v sigma 0 under root 1 by 2 I j dot I j dot dv plus integration, that is SL delta v tau ds minus integration st ti v I ds. So this is the complete equation, where the dot indicates the rate. The term kinematically admissible means that the closure velocity field should satisfy the incompressibility condition as well as upper bound condition. And the other terms are as where the j dot is the rate of work being done in the deforming body, v is the where small v is the volume of deforming body. Then epsilon ij is the strain rate in deforming body. It is taken that the epsilon ij are only plastic strain rates, while the delta v here is the velocity discontinuity on the surface, velocity discontinuity, that is SL, while Ti is the components of traction prescribed on the surface ST, and Vi is the velocity of here Vi. Ti is the component of traction prescribed on the surface ST, while the Vi is the component of velocity on the surface of ST. The right hand side of the equation is the sum of the different components of rate of work being done. For instance, the first term denotes the rate of work being done due to plastic strain rate. The second term gives the rate of energy or power being consumed on the frictional surfaces, such as interface with tool as well as on the surfaces of velocity discontinuity inside the body. The third term signifies the rate of work being done against the external applied traction. And for instance, in the cold rolling of sheets, back tension is often applied. The rolls pull the sheet against the back tension. The rate of energy being consumed due to back tension form the part of third term. So this is the equation for the upper bound theorem, and which has to be satisfied for our plastic deformation and velocity field to be formed, and we can calculate the die load as well. So this is about the upper bound theorem, and let us discuss next the application of upper bound theorem, that is the compression of a strip in plane strain. So in order to illustrate the application of upper bound theorem, we consider here a simple problem, that is compression of a strip in plane strain. When a long narrow strip is compressed, material flow is mainly in transverse, that is the width direction, and the very little flow takes place along the length direction. So most of material flow takes place in the transverse direction, that is about the width, that is about the width direction, and less on the length direction. So very little flow tracks along the axis of the strip, except near the ends of the strip. So this is a case of plane strain deformation. Now, as in the figure, a strip of length B, this is the length of the strip here, don't get confused, here length is indicated by the B, and width is taken as 2L, and height is described as H. Being compressed between two flat dies, we take capital O to X, then O to Y, and O to Z are the rectangular coordinate such that the OZ passes through the center line of the strip, and the origin O of the coordinate lie on the bottom face of strip. We take that the bottom die is stationary and top die moves down with the velocity of u dot. Therefore, the particle in the top layer of the strip moves with velocity equal to the minus u. It moves with the minus u dot as the top die moves in the downward direction. So it will the particles of the layer will move in the minus u dot. So particle of bottom layer have zero downward velocity. Here the velocity will be 0 because the bottom die is stationary. And for other point in the strip we take a linear distribution of the velocity and over the height of the strip, and the downward velocity u dot z of a particle A. Suppose there is a particle A from a height z, there is a z height, so velocity at that particular point is given by the minus u dot by h into z, and therefore the strain rate at zz is equal to the minus u by h. And as discussed above, there is no elongation along the strip axis. Therefore, the u dot y is equal to 0, and the strain rate epsilon yy is also equal to 0. Since in the plastic deformation the material is incompressible, so we have the xx plus yy plus zz strain rate equal to 0. Therefore, the xx is equal to minus zz is equal to u dot by h, and the particle velocity in the x direction may be obtained by the integrating the above equation. So if we integrate the above equation and the particle velocity in the x direction, ux dot is given by u dot by hx plus f of x and z, sorry, f of y and z, where y and z is the sum function of y and z, because x we find for x, so x will not come here. Now at the center line at x is equal to 0, ux dot will become 0 at center line, so this function will also become 0. Hence this will be equal to ux dot is equal to u dot by h into x. So the complete velocity field in the strip line is as we can be written as, for x the velocity field is u by h into x. For y direction it is 0 because there is no elongation along the center line along the axis. uz is equal to minus u h by into z. So the strain rate may be calculated by differentiating the velocity above velocity field equation, and velocity in the y direction is 0. It is taken the plane section before the deformation remain the plane during deformation. So the velocity in the x direction is the function only of x, and that is the in the z direction in the only of z. So therefore the strain rates are 0, and all the strain rates are can be written as xx u by h, yy is equal to 0, zz is equal to minus u dash by h, and xy, yz and zx all three are equal to 0. So now if we put the 3 of the right hand side, let the first term be denoted by the first term here, the WD is written by 2 by root 3 integration V sigma O into 1 by 2 epsilon ij p epsilon ij p raised to 1 by 2 into dV. So where here the sigma 0 is not function of coordinate. So by substituting the value of the strain rate in the above equation, it is simplified. If we put the value here, so it will be u dot by h square plus u dot by h square if we put over here, and the final equation will be WD dot will be equal to 2 root 3 sigma O U by H into V, and V is the volume of deforming body, and here it is 2 times L into H into B. So therefore here it is can be written as, if you put the value, so it will become the 4 by root 3 L B sigma O U dot. Now the second term is denoted by the WF dot is equal to S gamma delta V tau ds, and the tau is the frictional stress on the surface of velocity discontinuity. The tau frictional stress at the top and bottom interface between die and workpiece, we do not know the die pressure and we cannot use Coulomb's law of friction. So therefore we take the constant value of friction, that is tau is equal to mk, where m is the friction factor with value of 0 or to 1, and the value 0 correspond to the frictionless case, and m is equal to 1 stands for the sticking friction, and the magnitude can be written as the final, the WF is equal to 2 times m sigma O by root 3 after putting value UL L square by H into B. And the third term in the present case is 0 because no boundary force are applied on the slip face of the strip, and the rate of power by press is given by J dot is equal to P into U dot. So where P is the press load, and the average die pressure P average is determined by the dividing P to the contact area, which is equal to 2LB. So P average is equal to P by 2L into B, and P average is equal to 2 by root 3 sigma 0 plus M sigma 0 L by root 3 into H. So the first term on the right hand side denote the contribution due to the frictionless compression in the plane strain, and the second term gives the effect of friction. So this is about the application of upper bound theorem in the of a compression of a strip in a plane strain. Next is lower bound theorem. Now when a body undergoes plastic deformation, stress yield and a velocity field are set up inside the body, and the stress field so created satisfy the equilibrium equation and yield condition, also balances the external traction or tool force, Generally, we wish to determine the tool force, but since the actual stress field is not known, the external traction cannot be determined. Therefore, we construct a stress field which satisfies the equilibrium equation and yield condition. The rate of work done by such a stress field for deformation with a prescribed velocity is always less than due to actual stress field. This means that the calculated tool force or load on the equipment would be less than due to actual one. So this means in other words it would be written by the lower bound on the load, and the equation for this is integration SV Ti Vi dsv greater than or equal to integration SV Ti star into Vi dsv. The constructed stress field may be included an unknown parameter whose optimum value may be determined by the optimization of above equation. So this is the equation for the lower bound theorem, and there is only this information which is sufficient about the lower bound theorem. So this is it for today's lecture. Thank you very much for listening me carefully. Have a nice day.